Hello.
Hello.
Hey, Karen. How are you?
Exhausted.
Exhausted.
Yeah.
Yeah. How's your work other than the university? Is it getting worse
um,
or is the university work affecting?
the university work is being affected.
Yeah,
I'm just
it's
super
opposite.
busy.
Yeah.
Yeah. This people, I guess people still want their houses done while on break.
Hey, good morning.
Hey,
Good morning.
Avinash. It's a cloudy day. How is it in Cape?
It is also cloudy.
Yeah. Okay. Let's see.
I was curious about how to get access to Moses's talk today. She had mentioned that he was giving a talk.
Okay. So there are two options for that. One is I give you the access whenever I get the access, which will be 5 minutes before the talk. That's the easier and temporary method, or if you just want Moses talk. But there is also the option that if you're interested in getting that information every week, sometimes you don't want that. Okay. If you want it every week, then I can give your email to the person who sends the email, and you will start getting the information about the talk every week. And it doesn't mean that you have to attend it, but you will get the information. Does that make sense?
Yeah, I would be interested in the every week thing.
Okay, so then I will pass on your email to him. Do you want the message to come in your SIU email or private email?
Yeah, SIU would be good.
Okay, so I will pass on this information to the person. The person is the math faculty. His name is Kochik. Have you met him, or have you taken anything?
No,
or you know him?
I know him.
Yeah. So he is the person who pretty much organizes these talks. It's a reasonable, very informal, I would say. It is addressed to things that can be understood during that 1 hour. At least that's a hope, but it's usually hard to make everyone speak like that, or it's an art to be able to speak so that everything is conveyed in 1 hour. Most of us fail. But at least that's a goal, and people do try. So it should be possible. Yeah. So I will surely pass on that information. Yeah. And I can actually at least I don't have the actual information, but at least the information where it will get loaded, that's there. So because I did receive it yesterday night, so I'll pass that on to you maybe. Forward, right? Jordan.
So,
yeah.
Will you be going to?
Good morning, Moses.
Good morning, Moses.
Thank you. Good morning, guys.
Well, Moses, yes, Jordan, you were saying something.
Was it Sweden that you went to last summer?
Oh, New York. Sorry, what is that place name? Norway.
Norway. Yeah. Are you? Are there plans to go back?
Oh, that's interesting. It is all held off because I was supposed to go there in July this year, but they canceled all invitations in March, right at the same time as we canceled everything. So it's not that everything was held back until further notice, and there is no further notice, and I have this feeling that it may not work out this summer.
Gotcha.
Yes. And why in particular, like why did that come in? Moses talk and Norway?
I'm
Yeah.
sorry, in particular, why did what come in?
No, I was not asking you, I was asking Jordan. So any specific reason why you asked that, or just like that? Yeah.
Just of interest
Just
of
like
what the conversation we had first semester, just the progress of what you guys are doing.
Ah, I see. Okay, maybe it's completely doesn't strike me. You should remind me of what we talked.
You told me about what you guys were doing and studying while you were
Ah, I
there, and
see.
I was wondering if you do anything throughout the year. It's mostly just a summer gig, research
So
gig.
here is the point. I do it throughout the year, but the efficiency goes down by probably 100%. Okay, like if I'm able to do 10 things during the summer, I do one thing during the whole rest of the year. I do try, but yeah, it's hard for me to handle everything together. It's so that's why I have sympathies for your job, I suppose. I don't know how you manage the job and university together. I cannot. So there is a lot of currently what we are doing is that we are writing a new grant, and that's going on. So that's the current, and it might be not in Trondheim, it might be in Oslo. Like all the last many years I've been there, it's in the university called NTNU, which is in Trondheim for north of Norway. But now we are our basically the person in charge of all this is very old. He's 80-year-old, believe it or
Oh
not.
wow, wow.
So I mean, they did allow him to apply for this money even when he was 75-year-old. That was an exception already. But 80-year-old, I think they eventually said, no, we will have to stop this. So we are going to have him, but we are going to write the grant with someone else as in charge in Oslo. So we are going to change the university. So we'll see how it goes. Yeah. And there is a lot of uncertainty when it comes to money and applying for money. All that is in the we can talk about it later. Yeah, I'll be surely glad to. Yeah, so the answer is yes, we do it continuously, or at least my collaborators are continuously working, but I work practically speaking only during summer, but my mind is occupied in that all through the year. That's the way to put it. So I don't commit for anything during the semester.
Gotcha.
But I'm involved. Yeah. Yeah. Okay. So
Angela's in the waiting room.
oh yeah, she's in there. Yeah. How do you know? So do you guys also see the waiting room?
No, she texted me.
Ah, okay, good. Okay. Yeah, I think I was talking to Sharon. Sorry, Angela, we kept you waiting.
Yeah. Okay.
Okay. So now all of us are there, so I can increase the. Okay. Let's see what we have. I did take some decisions based on what you guys, I felt you guys were overwhelmed, especially Angela mentioned it. So I felt among you guys, I mean, with no offense or any bias here, I think Angela takes it. She should find the course easier than everyone else. But then she said she was overwhelmed, so I thought I should change my plans. So here is a plan. I'm not going to have the final exam this semester, so no final exam.
Okay.
So which also means that the grades that you have might work towards it. So does that? I felt it might be acceptable to everyone, but if it is not acceptable to anyone, someone thinks that no, final exam is really going to improve the grades. It's better to have the final exams. Then you write to me separately. Okay, you don't have to tell it here now. Think about it. Write to me, and then I'll reconsider this decision. Okay? Or I can even make it choice. I can have a final exam, and it's a choice that you guys take it or not. Okay. Is that acceptable or right away? Any comments? Do you
It
think that
doesn't
will
matter
help?
to me.
So it would just be the grades that we have.
Wrong.
You know, you would just everything that we've turned in and completed so far, including the
Yes.
second midterm and all the homeworks. That would go be the
Yes.
final grade.
That'll be the final grade. Okay.
Okay.
If you think final exam is important for your grades, then you write to me and we'll think about. Or I'll give a final. That's the point. It's just then it'll be optional. Whoever wants it gets the final. Okay.
Mhm.
And I was planning 2 more homeworks. I decided to have 1 homework, which will be due on the final exam date. So officially it will be due on Friday, but unofficially, because I'm not allowed to have any homeworks due beyond the final day of classes.
Mhm.
So it will be officially due on Friday, but unofficially you can take it until the day of the exams. Is that clear? So let me write that down. So again, if you think something else suits your grade better, let me know. Like since we are only few students, each person can get their choice of setup. Okay, so one is there will be only 1 more homework. I think it's homework 9, I suppose. No, I don't even write the homeworks.
It is homework 9. Well,
It is. So
I
we did
believe
only
so.
homework 9
on your
homeworks?
website, you only have 8 posted.
Yeah, so it will be the really. So we did only 8 homeworks. That's
We
pretty
lost
low.
2 weeks, so that should be, this would be
Yeah,
11
probably.
normally, or
Yeah,
9
yeah.
or 10 or whatever.
Yeah. Okay, so homework 9 will be due on May 1. That's a Friday. That's an official due date. Unofficially, it can go later. Okay, and no final exam. So we have only 1 homework remaining. Again, this dependent on like you guys. I think you guys worked sufficiently on your homeworks. That's good enough, and I don't expect that just by taking the final exam, you guys are going to significantly improve anything. It's only probably going to stress you out. So that was my decision. I don't know whether it's good or not. As usual, with all other decisions made by policymakers, in this small world of 5 people, I become the policymaker, so I might be wrong, but we will live with that. Okay. Okay, so any immediate comments or anything before I begin? Okay. So we are doing special relativity, right? So we want to talk about consequences or implications or consequences, right? Consequences of Lorentz transformation. Last time we said that relativity, the principle of relativity. The principle of relativity is that conclusions should remain the same for different observers in or different inertial frames. And an inertial frame is a frame that is moving with uniform velocity with every other observer. I think of infinite sets of observers standing at every space-time points in their own way, and they are all moving at their favorite speeds. And one person should see every other observer going with uniform velocity. So that's the idea of inertial velocity. In very simple words, a frame moving with constant velocity is an inertial frame. And relative principle of relativity is that all these observers should see the same physics. By same physics, we mean the equations like F is equal to ma. F is equal to ma is a physics. When I use the terminology physics, in Newtonian physics means F is equal to ma. Everything follows from that equation. If you're doing Maxwell's equation, we say there are a set of 4 Maxwell's equation. Everything that's related to that, that's derived out of that, that's the Maxwell's physics. Einstein's physics will be whatever comes from general relativity, that will be Einstein's physics. Quantum physics will be everything that comes from Heisenberg uncertainty principle and the associated Schrodinger equation, that will be quantum mechanics. So that's the language we mean. And what we are saying is that all this physics should remain the same in every inertial frame. But if we add, so if we also require that speed of light, c, or light itself is invariant whether everyone sees light the same way, right? C is, how do you say this? Light is invariant. Movement of light is invariant. How about that? Motion of light, movement of light is invariant. That leads to, so this plus this leads to Lorentz transformation. That was our conclusion last time. So terminology here, principle of relativity, again, means that different inertial frames see the same physics. Light means anything with speed of light involved in it. It could be a plane wave. Often we use the term photon, but photon concept does not yet come in. It comes only when you invoke quantum mechanics. So plane waves are the right way to think about it. So light, motion of light is the same. The word invariant here means, so there will be a difference between the words invariant and covariant. Invariant and covariant. Okay, so for example, invariant means this will exactly be the same. For example, a scalar quantity is an example. A scalar is an invariant under rotations. Okay, whatever idea we have of scalar, that number doesn't change. By a vector, we mean a covariant quantity. So its components can change, but its form doesn't change. It still is a vector, right? So a mu, like vector A, or let's call it a1 prime, a2 prime, a3 prime, going into a1, a2, a3, right? This is called covariance. So the components are changing, but that's okay. That's allowed. So this can change, but they have a specific way of changing, right? That's the idea of a vector, that they change in a specific form. So that's called covariant. Invariant means like a scalar. It's a number, it doesn't change. Okay, so that will be the two terminology we will use. So with those things in mind, Lorentz transformation in one dimension, if all the inertial frames are moving in the same direction, what we showed is so Lorentz transformation is let's say z prime and ct prime is equal to gamma times z minus beta times ct, and that's equal to gamma times z. What did I do? Help. Beta z, right? Beta z minus ct. Yes, that's correct. It is okay to have beta either way, plus or minus, and I will often use plus here. Okay, so I will put that as a plus in here, and this can be written as a matrix.
Are you?
Yes.
Is
please.
it supposed to be z? Is it supposed to be beta z?
Oh, is it not? Okay, help me there. Okay,
In
why is it not?
In our last class, we said z prime equals gamma z minus beta ct.
No,
And
beta gamma ct.
yeah, in our last class, we said minus beta ct and first.
Yeah, so this is how it was. Yeah, this is okay. Yeah, this is
and
minus.
c.
Minus plus.
Yes.
Is that correct?
Yes.
Okay. That's perfectly fine, but beta is a choice, right? Beta is, okay, so here the definitions of beta is
B over
equal
C?
to B over C, correct? And I can always start from minus V. Doesn't matter who says plus V minus V, so I can start with plus V and make it plus. Doesn't matter, I won't use it so much, so it doesn't matter. Yes, and if we use this in the last class, let us stick to this, okay? Nothing is going to change. So let's stick to that. It's completely symmetric. In fact, we use that fact in principle of relativity in the derivation of Lorentz frame. You use the fact that whether we go beta or whether we go minus beta, that's just a perspective. It should be, things should not change because of that. That means to say that if you guys are approaching me, you would say that I'm approaching you, and I would say that you're approaching me. Same physics. Okay, so that's the principle of relativity, correct? So it doesn't matter whether beta is plus or minus, things should overall remain the same. But let's stick to this beta with the negative sign here. And that's gamma is equal to 1 over 1 minus beta squared. And notice that I have this problem with writing gamma. So it's probably gamma better. Okay, so I'm learning. Okay. Okay, so that's the feature, and we said this can also be written as a matrix form. Sometimes it's convenient, or some people find it easier to see the symmetry in the system. So this is minus beta gamma minus beta gamma gamma, that's equal to z times ct. Agreed? Let's call this matrix L. Or yeah, so let's introduce a few things. Any questions at this stage? This is where we were last time. Okay. Let's introduce what is called a 4 vector. Okay. Or before that, what is a 3 vector? Like the usual vectors that we study is
just
what
a
is called
position
3 vector.
vector.
Just a position vector. What about force? Is that a vector?
Yeah.
Sure.
Right?
It has
It's a force. So
position.
how do you define a vector then?
Something with magnitude and direction?
Yeah.
Something with magnitude and direction. Good. Can we? Yeah, that's okay. Surely okay.
In three-dimensional space, like a three vector has components for each degree of freedom in space, but it doesn't account for any degrees of freedom in time.
Yeah. You get more precise, maybe. Yes, that's all correct statements. But there is a.
I don't know.
Not general enough. How about that?
Invariant and a
Spatial.
invariant and a
and-
rotation.
Yes, that's one statement actually can give you every other statement that you guys made. You can derive from that one statement, and that is that the length of the vector remains invariant. Now that we use the word invariant, that's what it means, does not change under rotation. So rotations is important. So vector has something to do with rotations.
But wouldn't that, couldn't you
Without
say the same thing about a scalar?
Yes,
So
scalar
what then?
is scalar as a number doesn't change under rotations as a number.
So how would you define with that statement something invariant under rotation as a vector or scalar?
So here is how we can do this. That's exactly the definition that we are going to use. We are going to extend this to Lorentz transformation. So the only difference will be, come on, move. Yeah. Okay. So let me use this space here. So what we are saying is, first that is, let me make it symbolic. So that is a vector A. Okay. So first let's say scalar, right? That is a scalar phi. That's just a number, right? Then there is a vector A. This has 3 components, right? This means that it has 3 components. Correct. Now this transforms. So under, so there is a rotation transformation, right? So let's say, and this can be, and there are higher forms of this. This is a tensor also, right? Let's say next one is a tensor, let's say. So tensor has 2 vector components if you want, or else the best is to write an I there, right? Yeah, actually, let me write the I, like index notation. This has 0 components. This has 3 components. This has 9 components. Clear with me? Right.
Yes.
So these are structures. Yes, Jordan?
No, I was just saying, yes, I'm with you.
Yes. Okay. Thanks. So now you make a rotation. So by rotation, we mean the physical act of changing the axis. You're rotating the axis of your coordinate system. By a scalar, we means its number will stay the same, like a temperature, right? Temperature stays the same. Okay. By a vector, what we mean is that this might change. These components will change, but they have a specific way of changing. Like it's not any arbitrary change. It's in such a way that the length of this vector remains the same. Okay. Same thing about a higher rank tensor. So this is gamma ij prime, and this will be all the 9 components. And what is the way they change? That's the rotation transformation. For example, ai prime will be equal to the rotation matrix ij times aj. How does a tensor change? That's 2 components. So it is gamma ij prime is equal to im or jn and gamma mn, right? I think of this symbolically. Each component, there is a matrix that comes and changes its component. This is easy to visualize, I suppose, for all of us here. There are 2 rotation matrices. If it's a 3rd rank tensor, there are 3 rotation matrices. It's a lot more complicated to write. It's a tedious work to go through the transformations, but that's what a tensor is. And there are quantities that remain the same, and rotation, for example, the easiest way to say is that a vector, length of a vector is invariant under rotations. That's the signature of the of the whole transformation. In fact, from that one statement, everything else can be derived. Okay. That's not obvious probably at this stage, but from that one statement, and that's what I mean by that, that if you multiply this with this itself, then that length will remain the same. And we will do that a little bit in Lorentz transformation here, at least a basic idea. With me? Did I clarify? Okay. So now, is energy a scalar or a vector under rotations?
It's a scalar quantity, no?
Yes, because it is work done. It is related to work done. Work done is the dot product of force and length, and dot products are invariant under rotations. Okay. Notice whenever I'm now using the word in this once special relativity comes in, I'm always saying vector with respect to rotation, correct? So by nature, by definition, a vector has to have a transformation associated with it. Now we are going to change our language. We are going to say a vector with respect to Lorentz transformation. Okay? So that's a new concept, a vector with respect to Lorentz transformation. It should be differentiated from the idea that a vector under rotations. Something that is a vector under rotations still stays a vector under rotation, but it may not be a vector under Lorentz transformation. Something that is a scalar under rotations may not remain a scalar under Lorentz transformation. Classic examples are important examples are energy and momentum and force, or for that matter, velocity. Every vector that you've seen actually in mechanics, they are vectors under rotations. They most probably are not vectors under Lorentz transformation. So we have to find those new vectors that are characterizes the Lorentz transformation. So let's go back.
So that's the 4
So
vector.
That's the 4 vector, exactly. 4 vector is a vector under Lorentz transformation, and the first vector we come across is C and T. So we'll show this as X, Y, Z, and there is a 4th component now, that's CT. Okay. Often we will write this as, actually, let me write this in the other way. So there is 2 ways of writing, right? I can let the time follow the position or have the time in the first 0th component. So, and both are used in literature. Either you can say X1, Y1, Z1, that's the first 3 component and time is the 4th component. Or you can say time is the 0th component and other 3 keep their numbers, okay? So this is the 0th component and that's the language we will use. And often we will also write this as CT and your old rotation vector, right? So this is the rotation vector plus a 0th component plus a time component to it. We will call it the time component. Even if we are not talking about time itself, like force doesn't have any time in it, but we'll talk about time component. The 0th component will be called a time component and the rest of the 3 components will be called the position components. This will be denoted by, now that there is 4 components, this will be mu. Okay? That's your language. Okay, so that's a 4 vector, 4 components, and it has a 0th component and a 3 components. This obviously mu runs from 0, 1, 2, 3. Often I, J, K, so I will run from 1 to 3. So general quantities are all Greek letters, mu, nu, alpha, beta. By default in this course will run from 0, 1, 2, 3. Okay. And all the, I think it's a Latin, so it's I, J, K, L, M, N. Right, they will all run from 1, 2, 3. Clear? So that will be our notation. For example, if I don't specify it, x mu, I don't tell you that what that is. X mu is immediately a 4 vector because I've used a Greek letter. Xi is a 3 vector because I've used a Latin index for that. Is that clear? We won't need it too much because it's only a 2-week course and that too 3 classes, but it's good to be aware of this. Okay. Okay. So this matrix, one more. So that is a 4 vector. Remember, a vector always needs a transformation. vector by itself requires a transformation to characterize it. Here it is a Lorentz transformation. Lorentz transformation is a matrix, so obviously it has two components. So we will also often call it L mu nu, right? Two components to that. So this is the vector matrix, transformation matrix, transformation matrix. Transformation should have come in the front. Okay. Of course, it is a tensor itself, but it's a defining. It's like the rotation matrix in rotations. Okay, that's great. So we can write this matrix transformation that we wrote above as x mu prime is equal to L mu nu x nu. Okay, doesn't matter what that means. Let's let's even forget the index. And since it is z, let's call it z prime. Z prime as a vector is equal to L times z, right? So this is a vector, right? Z, it's actually a little confusing, right? How do I say this? Help. Yeah, let's write x mu. X mu prime is equal to x mu. Okay. So the transformed quantities symbolically are got by transforming the original vector. Okay.
So before you wrote x mu subscript, is that something different, or is it the same thing?
It is the same thing, much more, a lot more rigorous. How about that? I change. This is a lot more rigorous. This is a true statement. No one can, like, this is, once we know the notation, then this is a very rigorous statement. The other one is symbolic. What that means is that L operates on X to give you X prime, right? This matrix transformation, nothing more than that. This is this, okay? But I don't want to get into the intricacies of the index notations. I'm just avoiding the whole thing, okay? So the index notation that we will use will be very primitive because of the time constraint, okay? So here is the only thing we will need for our purpose. I defined already x mu as ct and x, correct? That's our 4 vector. We will call it the contravariant 4 vector. So this will be called a contravariant vector. It doesn't have to be a position vector. It could be any other 4 vector. It doesn't even matter what it means. Contravariant, the word doesn't really matter. What is important is that mu is in the superscript. In the same place, I define a subscript, or what is called a covariant vector. And it is got by switching the sign of the time component. It's just easier to manipulate things using this notation. That's the only thing we know. This is what, if you have done a math methods course, then this comes out in a much more general form. You can define this in a much more general way. But for our purposes, only thing we need is that to go from the contravariant to covariant, I need to switch the sign of the time component of a vector. In this case, it is the time itself, but it could be any other 4 vector. Agreed? Clear with me till now? That's the only definition I'll need. So let's define the length of a vector. So length of a vector in rotations is just got by the dot product. So I have to define a dot product in Lorentz transformation. So here is how you define a dot product. So let's have a vector a mu. So just to get oh, I have to move the. Is that?
Yes.
Yeah. Thank you. Thank you. Yeah, we forget. Okay. So a general vector would be a mu will be a0, correct? And a vector a. That's a contravariant vector. Covariant form will be with a0 on top itself. This is minus a0. This is also equal to a0 of a. So the idea is that a0 is equal to minus a0. So the
Could you raise the
spatial
board
indices.
just slightly? Just slightly.
Oh, the
It's close,
setting is
but
bad. Come on.
there we go.
I'm moving the camera instead of the
That's okay.
remote.
That'll
because
work. That'll work.
hold on, let me. I think it just collapsed down. Better. Did it work?
Yes. Yes. It's perfect.
I think by the weight of the camera, it eventually in a few days it went down in the last 20 days or so. Okay, good. So notice the 0th component change when you go from superscript to up to down, but the spatial indices doesn't do anything. Like remember, Latin is from 1 to 3. These remain the same when you go from up to down. 0th component changes sign. That's the only key. Okay?
Okay. Okay.
Now, a length of a vector, square of the length, will be defined as, this will be a0 square or minus of a0 squared plus a dotted with a. Is that clear? Notice the minus sign. That's the, you can say, complication or richness, right? Two ways to very opposing ways of viewing the same thing. This complicates it significantly, or it makes the whole concept very rich. So, so the length of a vector in rotations is pretty straightforward. It's the length of a vector. This negative sign now makes length to be negative, right? This is a length, so this is actually allowed to be negative, or length square, let's say. Length square is allowed to be negative. Otherwise, it becomes complex, right? If you talk in terms of length. So that's the length. Now, why in rotations, length remains the same. So we should prove that this actually remains the same. So let's go back and so any, oh, by the way, I should say any, let's say this is the z component. So this is prime a0 prime. That's equal to beta gamma. Like in rotations, once position vector, like Avinash started by saying position vector is a vector, or position is a vector. But then anything that behaves like position under rotation is also a vector. Like force transforms exactly the same way as position vector under rotation. So that's the idea, that even though I have not specified what A is, that also transforms the same way. AZ and A0. That's the idea of a 4 vector now. Okay, so and that will be the transform. I don't care what these A's are. If they transform by Lorentz transformation, that's a 4 vector. Okay. And let's calculate, and that is X and Y is also there. We are keeping things simple, only keeping the Z component here. X and Y are just spectators here, but in general, that should also be brought in. So let's calculate what is minus a0 prime square plus az prime square. That's the length of the vector, right? According to our definition, there is of course x and y, but we are saying x and y remains the same anyway, so that's not going to change. So that's equal to prime is minus of minus beta gamma times az plus gamma times a0 square, and then plus gamma times az minus beta gamma times a0 square. Right. So that's equal to, let's collect the a0s first, because I would like the a0 there. So that's minus of a0 square, right? A0 square has a gamma square to begin with. That's coming from the first term, and this one has beta square gamma square, and that's, since there is a plus, I've already put a minus outside. That's minus beta square gamma square, right? That's a naught square. Then the az square has plus az square. Again, there is a beta square gamma square, and then there is gamma square, the same coefficient, right? Gamma square minus beta square gamma square. There are cross terms which exactly cancel out, right? There is a minus of this, but the front signs are different, so the cross terms cancel out, right? Same thing happens in rotations also, by the way. What is gamma square? So this is equal to, let's calculate what is gamma square minus beta square gamma square.
That's just 1, right?
That's just 1. Is that clear to everybody? Gamma square minus beta square gamma square is just 1. Right, so let me write that down here. So gamma square minus beta square gamma square is equal to 1 minus beta square times gamma square. Still in the board space? Yes. But gamma square is nothing but 1 minus beta square, so that's equal to 1. That means to say that this is minus a naught square plus az square. So the length, whether I go to the primed frame or to the original frame, remains the same. Okay. And that plays a very crucial, that's the basic idea of special relativity always, right? That is, like anything we do, we want to keep with that as a picture. It's a length that is important. The components doesn't matter. Okay. Any questions in this derivation? Same thing can be done for rotations also. As an exercise, you should say that how does the components of a vector change under a rotation, or length of a vector change under rotation. Okay.
So
Good.
contravariants have proscripts or whatever, and then covariants have
Contravariant is the superscript, covariant is the
yeah.
subscript. Doesn't, again, that's just a detail. The important concept is that the length got by multiplying the two, which is just got by putting a negative sign in front of the length square. Forget the contravariant, forget the covariant. Think of the length of the vector as square the time component, but time components get a negative sign.
Okay.
Square the spatial components, they get the positive sign. That's the length of the vector. That's the only important thing in relativity. I mean, I mean it. I mean, I'm stressing on that, and I'll tell you in a minute. All the basic concepts will come out of the basic standard thing about the relativity, that things change, like length contracts, time dilates. So what is time, right? If time is changing for everyone, what do you mean by time? Right? What do you mean by space? Like, so that's the big paradoxical part of relativity, but that's here is the point now. Okay. So let me come to that. Hopefully I can clarify that. Okay, so let's go about rotations, right? So So this is rotations. Okay, so this is X and Y. If I were to make a small change in the axis, that's what rotations means, right? I can measure in terms of X and Y or X prime and Y prime, right? I can make a small rotation to this. That is a vector which has a meaning as a length and a direction, correct? That's how we understand a vector that has a length and the direction, right? Now suppose there was a person who was measuring the X component of this, and there is another person who is in the rotated frame measures AX prime, correct? So you measure the X, so the goal is to measure the X component of a vector. So Moses goes to his lab and measures the X component of his vector. Jordan goes to his lab and measures the X component of the same vector. Okay. And they report in independent journals that I measured the X component of the vector to be 5 newtons. Jordan says he measured it to be 15 newtons. That's a significantly different result. And you say that, oh, this must be wrong. There's something completely wrong going on. I'm getting 5 newtons, he's getting 15 newtons. Is that a meaningful discussion? Is the point clear what I'm trying to make? So
We're measuring something different.
exactly, right? You never specified which axis you're talking about. There is no one telling you that, correct? You're measuring X component of this, you're measuring X component of that. There is no guarantee to be different. That's okay. We are going to be different. In fact, you should use your rotation transformation to say that, oh, your axis is rotated, and if you rotate 5 newtons by certain amount, you will get 15 newton, and it will exactly come out, right? That's the idea of space and time in relativity. Never measure spatial distances. Never measure time, right? So same thing here now. Let's say in relativity, what is happening is, now we have a z, correct? And now there is time instead of X and Y, correct? Or it could be any other component of a vector. Let me say AZ, some vector AZ, right? And some vector A0, component A0. If I rotate this, rotation is going to be slightly different in here. Its geometry is different because of the negative sign, but very naively speaking, it's rotated in this manner, but actually it doesn't rotate this way, it rotates the opposite way. We'll talk about that later, right? So that is again so actually, let me be precise here. So the rotation actually makes it like this. How about that? Okay, it has a weird rotation. Okay? The axes don't go that way. One axis comes to the left, the other goes to the right. That is just for you guys to get curious. Why is that? Think about it another time. Let's not get that. Okay. So that is a vector here. We call it a mu now, right? Not with the symbol. And again, there is someone measuring AZ. There is someone measuring AZ prime. They shouldn't compare it as a numbers. They have to transform it. That's length contraction. That's time dilation. If you measure time, you have to dilate it. Or you have to use Lorentz transformation to change it to whichever frame you're measuring in. Right? Time is not going to be the same. Your age cannot be compared. It's meaningless to compare ages strictly as numbers. It's meaningless to talk about length strictly as numbers. They transform. But there is a invariant length. So if you want to compare, there is an easier way. Nothing wrong in comparing ages, nothing wrong in comparing distances as far as you transform each other. But there is an invariant length here, right? There is, what's the right thing to do in rotations? Oh, we are going to measure the length of the vector, right? AX square plus AY square. This is the quantity you should compare. Whichever frame you go and compare, that will come out to be the same. Same thing you do in relativity. Compare a naught square plus a z square, and that will remain the same. That's an invariant length of the vector. That's what you should, that's the easiest thing to compare. Then there will be no issues, no transformation needed. In whichever lab you go, you will measure the same thing. Okay, that's the basic idea. So then all the confusions go away. And what it will turn out is that, so the classic examples are, of course, so this is a kind of summary or a quick glimpse of what we are going to see. So there are 4 components, right? It's not the space and time. Oh, I didn't move it in the right place. Come on, move.
Maybe because you moved the camera before? Adjusting the height?
I don't know. Come on, move, move, move. Oh, that, yeah, I did move it. Oh, shoot. Okay. So I did move it. Okay. Bad thing to do. Okay, so now I have to manually control it. Okay, not bad. So let me set it. What do you do? Setting 3 set. Okay. Okay. So what was I doing? Oh, yeah. So it's meaningless to talk about time. It's meaningless to talk about space, but together, space and time have a meaning. Okay?
So the space-like components are rotated and the time components don't change. They stay the same?
No, time components also change. Remember Lorentz transformation, time component changes.
Okay.
Right? Time component, so how does time component, so here is how it changes, right? So x prime, let's say, think of it as just z, right? Z, let's say, z prime is equal to gamma, right? Gamma times z minus beta gamma times ct, right? That's how it changes, correct? And time also changes, time changes. Right. So
Okay.
it is gamma, sorry, minus beta gamma times z plus gamma times ct. Changes.
Okay.
It's complicated to think in terms of time and space individually. Nothing wrong in it, but then you should be comfortable with rotating things. But it's easier to just measure the length of that. Right? Length of this Lorentz vector, Lorentz 4 vector, and you're good. Compare that and great. This is the easier way of doing it. Okay? But what are the others? If you're talking about velocity, what is it that comes in? So you have to think, so this is position and time. What about velocity? So this is velocity. And let's put gamma. Put in a gamma there, right? That's a gamma, my gamma. And you put c times gamma.
So is this all in that, is this all in like the Minkowski space?
Yes, this vector, 4 vector that I have talked about, right? I didn't use the terminology, that's called the Minkowski space. The space time associated with this 4 vector is what is called the Minkowski space. Perfect, great. If you're aware of that, okay? That's the keyword you want to search for. This all properties that we are talking about is valid for anything in Minkowski space. Okay, clear?
Mm-hmm.
So we should always know which components go, like it's good to know what this 4th component is, that's the point, or the 0th component is, right? For velocity, it is the speed of light itself. Like, amazing, like speed of light is the 4th component of velocity. There is a gamma factor also in there, but notice the nice feature there, the speed of light is the fourth component of velocity. And most interesting is momentum, which is going to change. Energy is actually the fourth component of momentum, or the zeroth component of momentum. That's the new big deal in relativity. And energy and momentum are reasonably separate. One is scalar and one is a vector. And in Newtonian physics, now energy and momentum are part of the same vector. So now I come back to that question I started with: is energy a scalar under rotations? I asked a question before.
You asked if energy was a scalar or I forget.
We said, yes, we said we agreed that energy is actually a scalar under rotations and momentum is a vector under rotations. But energy is not a scalar under Lorentz transformations. It's a zeroth component of a vector. Okay, it's not a scalar. It transforms. Energy is going to transform because it's a zeroth component of a vector. Momentum is not going to remain the same. If you measure in a different frame, it will come out to be different. Energy is not going to remain the same. If you measure in a different frame, it will come out different. What will remain the same is the length of this vector. Okay, and guess what? What's the length of this vector? The length of this vector is minus e square over c square plus t square, correct? That's the length of this vector by the construction we have, negative of the time component and the plus of the position components. That's the length of the vector. And the amazing part is that that's the mass. That's the mass of the particle. So this is m square. Actually, that is c square also, up till a mass, up till a square. Okay, so that's m square c square. So mass, momentum, and energy get related in, sorry, that is a negative also. Okay. Mass, momentum, and energy get related in relativity. This is the summary of what we are going to see in the next two classes. So that's kind of peek into what we are going to see. We are going to develop that and why that's going to be that. Okay, we will do it in a very, very intuitive way. Okay, but that's the summary of your whole physics there, or relativity physics there. Yes, Jordan, you wanted to say something.
Oh, I just remember it being. Oh, okay, never mind. I just remember it being e squared. I remember the energy momentum relation. C squared momentum.
Yeah, this is often written as, maybe you're saying e square is equal to, this is often written as p square c square plus m square c raised to 4. Is that what you mean? Or sometimes it's also just written as E is equal to mc square, right? In this way of writing it, the mass has momentum in it. I will try to avoid this whole thing. It's confusing. M in this class will always be a quantity that does not change under Lorentz transformation. You can actually say that mass itself changes by including it within the momentum itself. So that's, I feel, a little confusing, but the half of the textbooks that prefer to do that. So obviously
it's the invariant mass.
Rest mass, you can say. So the point is, if you want to go from here to there, if you set momentum to be 0, you reach here, right?
Okay.
So m here is a rest mass.
Okay.
That means in the frame that you're when you're at rest, that's your rest mass. But in my way of doing it, m will not change at all, whether you're in rest mass or any mass, it will not change. The price is that the equations become a little messy. So for example, instead of having a neat E is equal to mc square, you get E square is equal to p square plus m square c raised to 4. But then there is information in there that there is momentum in there. So most of the advanced textbook will deal with this. most of the early popular level textbooks where you want to avoid algebra, avoid more variables, then you will use E is equal to MC squared. That's the simple way of saying it. Okay, clear? Okay, so we want to make this a little more precise about the what Jordan said, Minkowski space.
Third vector, like the first vector would be like a position 4 vector, and the second
is a position 4 vector. That's a velocity 4 vector. This is a momentum 4 vector.
Okay, got it. Yeah.
Right. There will be every vector you have studied in mechanics has a corresponding quantity in relativity. Position vector, velocity vector, acceleration vector, force 4 vector, momentum 4 vector. Electric field and magnetic field get complicated, they become tensors. There are no more vectors. They become tensors.
Got it.
Electric potential, they have a 4 vector. Magnetic potential, they have a 4 vector. Everything, most of what you can think of, they generalize. And the key feature is to find what is that generalization. That's the hard part if you're in an unknown territory. Here, Einstein already did it for us, that this is what the 4th components are. But if you're in a new territory where no one has yet explored it, then you have to figure out which is the 4th component. What behaves like the 4th component? So that's the challenge part if you're in the new territory.
So even like 4 entropy is a thing.
Like yes, 4
like,
entropy. Yeah. Let me tell. Yes. 4 entropy. Hold on. So I'm thinking, what's the entropy? Will surely be the 0th component of something, because give me a second. Temperature, right? T times TdS. Where does temperature fit in here? Hold on. Yeah, the point is temperature gets related with time. Okay? You can think of it as, yeah, I won't be able to answer this properly. It becomes an imaginary time. Temperature behaves like an imaginary time. Good question. Okay. I think I feel safer to say, I don't know. Okay. Even though I use it, I don't want to say anything wrong here. Okay. So that's a question. So these are the questions that come up, but this is solved. Okay. I know that this is solved. I even use it, but I don't think I can make that statement. I can explain that very well. So the question Jordan is asking is where does entropy fit in as a 4 vector? What is its 3 components? If it is a time-like component, what is the 3 vectors? And if it's a vector, what is its time-like component? Yes, good question. Entropy will be like energy, I would think, with respect to the temperature being taken out. Yeah, I don't know. Okay, let me. Certain things you can leave open, right? I'll let you explore. How about that?
Okay.
What you can search for is relativistic thermodynamics. It's a well-studied topic. Yeah. You asked in the beginning, or I mentioned something about the 80-year-old person in Norway, right?
Mm-hmm.
He is a world expert in relativistic thermodynamics. So that's a sort of, yeah. So there's work related to that in 50s and 60s. Yeah. Good question. I don't know. Okay, let me proceed. Okay.
Okay.
If you allow me. Yeah. Okay. Sorry about that. Good question. Yeah. Okay. So let's go back to 4 vectors, and let's go back to the length of a 4 vector, right? And in fact, let's work with position and time. This generalizes to any any vector. Let's define, so that is d minus c square dt square plus dx dotted with dx. Right? Instead of time, I'm talking about differences in time now. Okay? It doesn't specifically matter. Think of, so this is ds square, right? You can also think of this as minus c square t square plus x dotted with x. This is with a single vector. This is difference between two vectors, two close by vectors, so that you get dx, dx, and this would be s square in that case. Perfectly valid quantity. Sometimes we will also say delta x and delta t. That means it's not infinitely small. If it is infinitely small, then you make it a differential. If it is big, then it is delta x, right? Clear? So this will be called a, what's it called? What was it called? Oh, proper, yeah. Proper, proper length. So S or ds, right? This will be the proper, S is called the proper length. Sometimes it's also called proper time, but then it has to be minus. Okay, so sometimes, so the proper time would be minus c square tau square. Right? So these are definitions, right? So tau is proper time. We'll see what it means in a minute. Okay. Clearly, s square can be greater than 0, s square can be equal to 0, or s square can be less than 0. Correct? It is 2 minutes to 10:50. I'm going to take extra time.
That's fine.
Okay. Okay. So the length of this 4 vector can be greater than 0, equal to 0, less than 0. When it is greater than 0, notice what is dominating. If you have square of 2 quantities coming and it has to be greater than 0, that means the space part is dominating. Correct? So then you call it space-like vector. If it is less than 0, that means the time part is dominating. Then you call it a time-like vector. And if it is exactly equal to 0, what will you call it?
Light-like.
Light-like. And why is that?
Because light moves, how do I say this? Because light makes 45 degrees, means it bisects the space-like and time-like.
Diagrammatically, that's correct. You're seeing it diagrammatically. Good, that's the correct answer. But if this is equal to 0, that's the equation of time, right? That is x squared is equal to ct squared. If you remember, x equal to ct was the equation of time, right? That describes the equation of time. So that's light-like. Okay, but that's a correct answer, Avinash. Good. So that's light-like. If you want to see it in a space-time diagram, right, so this will be our space-time diagram, and for conventional reasons, the space part is usually on the x-axis. It's not necessary. It's usually different from what we do in mechanics typically. Z is on the y coordinate and time is on the x coordinate. Here, Z is on the x coordinate and time is on the y coordinate. Okay. So if you had things at the origin, so this will be a space-like vector. that will be a time-like vector, right? Because time component is bigger than the space component. Is that clear? Like this is space-like S, let's call it. This is T. Because the time component is bigger than the space component, right? If I were to take the components here, this is longer than the time, and here the time component, if that helps, is larger than the space component, right? And if you're really on the 45-degree axis, as Avinash pointed out, then the space and time is exactly the same, and that will be equal to 0. Okay, clear? Any questions there? Probably. Have you guys seen this description of space-time before?
Yes.
Yeah. So here is a question. It's a slightly misleading question or tricky question, so be careful, but not very hard to answer. Here is a vector, right? That's a vector I've shown, right? That's the length of the vector. That's the tail of the vector. That's the head of the vector. Is that a space-like vector, time-like vector, or a what's the third one? Space-like, time-like, and light-like vector. So this vector, and again this is Z, and that's CT. Is that vector space-like, time-like, or light-like?
Is it time-like?
That's a correct answer, right? So the only misleading tricky part here is that it is in the space-like region that we typically associate a vector with, but that's not where it is. You also always remember, even in simple mechanics, right? Tail has to be kept at the origin. You have to move the origin to its tail, right? So move the origin to its tail. So that's your axis. So this is usually how you will represent it. That's your time cone, right? So it's in the cone, inside the time cone, right? So well, that is talking about the cone. So this is how space-time is usually referred to as. If you are sitting here, that's your present time. So that's your present. This is future. That's past. Okay, every vector that falls in this is future. That's every vector that represents some way or the other a past. And there is space-like quantities here. And we will talk about that. Just to give you a feel, every space-like vector anywhere can be made into present. Okay. Everything in the space-like region is basically present. And we'll talk about that in a few minutes. Okay, that's the non-triviality of time having a transformation. So now this would have moved. Better. Okay. So let's think of a space-like vector. Right, space-like vector. And a classic example of a space-like vector is, so this is a time cone, right? And this is a space-like vector, right? That's S, let's call it. Okay, S mu if you want. Like it has a time component and a space component, and the time component is smaller than the space component. Okay, so that's a time-like vector. We are interested in its length, so it is C t square. So, or let's call it S0 square minus plus vector S magnitude square, correct? That's what its length is. And we know that space-like vector, will it be greater than 0? So it's greater than 0, right? But in another frame, this will look like minus S0, correct? Prime square plus vector S magnitude square. Correct? I can always choose a frame. See the note, this is the kind of arguments you use in relativity. There exists a frame such that prime is equal to 0. Out of all the possible inertial frames, I can choose an inertial frame, or there exists an inertial frame in which S0 prime is 0. The only condition is that this has to be greater than 0. That's the only condition that's needed, correct? So let's say this is delta S square, right? This has to be greater than 0, and which is satisfied even if this is 0, because that's a positive quantity, correct? So there exists a frame in which this is 0. That's minus S0 square plus vector S square is equal. So this is primed, notice it's not the same length. This is this primed length square. Right? That particular length is called the proper length. If it's a space-like vector, there is a quantity called proper length. If it is a time-like quantity, it doesn't have a proper length. There is no meaning of proper length. If it's a space-like quantity, there is a meaning called proper length, and it has no meaning of time component. Time component has no meaning. You can get rid of it completely. A space-like vector in Lorentz or in Minkowski space or in Lorentz transformation has no meaning in time. You can always transform out the time if you want. So what is the meaning? Let's go into space and time, which is more meaningful. This is for an arbitrary case. So let's talk in terms of space and time. This could be minus delta t square plus a length square, right? So let's say x, magnitude of x, delta x square is equal to delta x prime square. Let's make the interpretation here. On the left hand side, this means that there are two events. This is the difference between the two events. This is the length between the two events, correct? It happens in a time delta t, correct? So think of let's say what's the counterintuitive statement of simultaneity? Yeah, so let's say no good example coming up.
So our space-like vectors, they're basically the second event that happens is outside the light cone of the initial event.
No, this is just if you move the vector to the origin, its head will be in this quadrant, or it could be in this quadrant. That's
which is outside of the light cone itself. The vector is outside the cone of light.
Yeah. This is the light. Yes, that's correct. That's the light cone. Good. That's correct. Yes, so it's outside the light cone.
Now, if it was time, the event would be inside the light cone.
That's correct. If it's time-like, it will be inside the light cone. That's correct. Okay. But now this has a space-like has a very big character in this. Notice on the left-hand side, there are two events happening, and there is a time in between them. It's like saying the train came to Carbondale and the train reached Chicago. That could be the two events: train crossing Carbondale station, train crossing Chicago station, correct? That's the time that elapsed between them. Agreed? What's the time in the same event has been measured in a different by a different observer? What's the time it took? Right, that's 0, right? This is 0. So it happened simultaneously, which is impossible, right? So typical world-like events, motion of things cannot be space-like. That's the conclusion. But there are vectors which are space-like, but they cannot represent motion. That's all. For example, force will be space-like. Okay, force turns out to be space-like. Okay, but it doesn't mean that you cannot have space-like quantity motion, which is what has to do with causality. That's usually always like simultaneous. Like what we have said here is that simultaneity has lost its meaning. Something that is simultaneous in one frame, move the frame, you lost the simultaneity. Twins are no more interesting because it depends on the frame. Okay. Twins born in one frame were simultaneous. In another frame, they won't be simultaneous. Okay, so simultaneity doesn't exist, is not a is not invariant. Is not invariant. By invariant, I mean it will be different in different frames. It's like time itself. Like time itself it changes, correct? So simultaneity is event that we are so used to, that something happens at the same time between you and me. That's not a invariant quantity. Big. So this is the first big counterintuitive conclusion that you come in Lorentz transformation.
Is this only true for space-like vectors?
Only for space-like events. Yes, that's correct.
And motion doesn't happen.
In fact, even in time, or first of all, simultaneity is possible only in space-like event. You cannot have simultaneity in the time-like case. That's the conclusion. But if it is there, it is not invariant, right? Okay, simultaneity is possible only in space-like events. Okay, but in the time-like, if it is 0 in one frame, it is 0 in every frame. That's the way to put it. If that is simultaneously in a time-like case, it has to be 0 everywhere, in every frame. We'll come to that. Probably I'll talk about it. Okay. Now, so with time in mind, let me take 5 more minutes and let me talk about time-like also. Okay. So time-like vector. Notice, by the way, before I proceed, this kind of argument is a new kind of argument. Typically, we don't use this in physics so much. I mean, it's not that you cannot use it. It's not very common to use this argument, but these arguments are very common in relativity. We were in one frame, go to another frame, prove something, come back to this frame, right? So choice of frame becomes crucial in or things become tremendously easier if you're measuring or if you're calculating in the right frame. So go to the particular frame, do your calculations and come back. That's the logic we are using. Oops, moved again. Okay. So time-like event, similarly, now this is the time cone, correct? Now we say that minus c square delta t square plus delta x square is equal to minus c square delta t prime square plus delta x square. time-like means that it is negative, so it is possible to have a frame in which it is purely time-like, so that's delta t prime square. Correct? So now notice the Moses argument that let's say that t prime was 0 in one frame. Like it's a time-like vector, and we say that it is 0, it is simultaneous, right? If it is 0 in one frame, I got to have it 0 in the other frame also, because now it has become a light-like event actually, right? So it's not even time-like. So in principle, it cannot be 0. Right? This cannot be 0, because if this was 0 in one frame, then you're not simultaneous, or it's not time-like event at all. Or if it is 0 in this way, then you say then it is space-like. So you cannot have a simultaneous quantity in time-like. So I think I was not seeing through completely. Yeah. But now we can make one conclusion, that if you were to make it purely time-like in a frame, then any other time that you measure is going to be smaller, right? So you can say that if this, so if you put it, write it in this form, so this is c square t square minus dx square is equal to c square delta t prime.
So that's
So
the
this is-
positive. That's the upper half of the cone.
Yeah, the whatever I shaded is the upper half. Is that the question?
So the positive time-like is top, and then the negative time-like vectors are the bottom half, right?
That's also correct. That's correct. And usually we say future-like and past-like. That's also a common terminology. Okay, helps? But I'm not using that in this discussion. I'm not differentiating future and past as
Okay.
of now, maybe in a few minutes. Yeah. Here, what I'm trying to say is that let's say that in a frame I chose, I made it purely time-like. That's the maximum length I can have in time. In any other frame, or sorry, minimum length I can have in time. In any other frame, delta t has to be larger, because subtraction of a positive quantity is giving you this. That's the idea of time dilation. Time always dilates, right? From the maximum, or let's say minimum amount of time is in this frame. In any other frame, time has to be larger, because the subtraction of that has to give you this, right? Time always dilates if it's a time-like event. Like time has a meaningful statement only in time-like quantities, and in that case, this is a time dilation. In the same spirit, if I were to talk about length contraction here, if this is the maximum length possible, everything else has to be smaller, right? So, or this will be the maximum length, and this will be the contracted length. So length will contract and time will dilate. There is a little more to that. We have to talk about what exactly we mean by length, how are we measuring it, but let's not go in there. The basic idea is that length and time do not remain the same. That's the prime point. What I have not done is that what Jordan is alluding to is that that is a crucial thing, that time always runs forward, right? If I measure time to be moving forward in one frame, I shouldn't be able to transform and get it time moving backward in the other frame. Okay, that doesn't happen. And for that, one way to proceed is go back to your Lorentz frame itself. So this is, sorry, Lorentz transformation itself. So delta t prime is equal to, right, c times delta t prime is equal to gamma or beta gamma times delta z. And so there is a minus if you want. So that's minus plus gamma times c times delta t. Let's say delta t is positive on the right hand side, right? And one has to argue that beta, remember beta can be positive or negative, And delta Z can also be positive or negative based on what you are talking about. But if it's a time-like vector, one has to argue that irrespective of this, if delta t is positive, delta prime t prime is also positive. Right? So for time-like events, time-like vectors, if delta t is positive, then delta t prime is also positive. So that has to do with the causality. If you shoot the bullet and someone dies, that's what happens on Earth, around us, you cannot change the frame and change the sequence of events. Right? You cannot die first and then get shot by a bullet. Okay, so the sequence of events cannot change in relativity. So that's causality. That's called causality. Relativity does not allow it. And most of the physics that we know does not allow it. But we do discuss it a lot. And it will be interesting if that's violated, because there will be a lot of consequences associated with that. But the expectation is that most of the pillars may not change. The causality will be preserved, I think. Okay, so what else? Okay, I had a list of things I want to talk. So length contraction, direction of time is invariant. Invariant distance, yeah, pretty much. Oh, there is an invariant speed also, but that's right there in the, and there is a speed limit also, yeah. Okay, but that's all minor things, yeah. From next class, we will actually do the dynamics or the kinematics of special relativity. We'll go through, it'll be more algebraic, less intuitive or thoughtful like today's lecture. Today was more qualitative. But reasonably logically correct, but we had to use a lot of logical arguments. But next class we will use algebraic ways to proceed. Start from 4 vector and get velocity for velocity, then differentiate it. So that's what we do in kinematics, right? Start with position, differentiate to get velocity, then differentiate to get acceleration. Then we get F equal to ma, right? That's the 4 steps in kinematics, introductory physics. Same thing we have to do. 4 vector, differentiate to get 4 velocity, differentiate to get 4 acceleration, and write Newton's law. And
so is it possible to transform time-like into space-like and space-like into time-like?
No,
No?
they're orthogonal. Okay. They're orthogonal to each other.
Okay. Okay.
Like it's like, can x-axis be switched to y-axis? No, like they're orthogonal to each other.
Okay.
One cannot be put into the other. If you are space-like, you are space-like. That's it. You can transform it and make it purely space-like, but nothing more than that.
Okay.
Space-like cannot become time-like ever. They have different nature. They're different signatures. Sorry, I took a lot of extra time, especially Moses, I think, has to give a talk. Probably he's really wanting to get out. Yeah. So Moses is giving a talk today at 2 o'clock. Maybe you guys will be interested.
All are welcome.
2 o'clock. So yeah, I don't know. You should ask Moses for how to enter the room, enter his talk. All right.
I can forward the Zoom link.
Yeah.
Sure.
Yeah.
Dr. Shajid, I was wondering if you
Yes.
can shift the EMTD class to Friday again, because I have kind of like a presentation with my quantum group tomorrow, and then I don't think I'm prepared enough.
Talk to Justin. There's only one person, right? Yes.
Yeah, that's why. I mean, if you can't, you guys can just carry on with the class. I'm okay with that. But if it's viable option, then
yeah, it should be okay. He seems to be having a flexible
like
schedule, and he's usually fine. Yeah,
as usual.
Seems okay to me.
Yeah, let me text him.
Yeah. Okay. Let me know. Sounds good.
Okay. Bye, everybody.
Okay, good. Yeah, enjoy. Yeah.
All right. See you guys.
Okay.
See you, Moses.
Good luck.
Good luck today.
Oh,
Yeah.
So,
Oh,
but
what?
Jordan, you'll be there, right? You said you'll be there. Yeah.
That's the plan. I have my help desk hours that nobody ever shows up to. So it's usually when
You can simultaneously go into, but probably you cannot go into 2 rooms simultaneously, right?
Well,
Well,
one is a virtual classroom, and the other is a Zoom room.
Yeah.
Oh, perfect. So then you can be logged in both ways. So anyway, the other person is not going to show up.
so as long as I don't, yeah. Well, I've only had 3 or 4 people since we've started doing this.
Yeah.
So we'll see.
In fact, you can do it simultaneously, right? If someone shows up, you mute yourself for both camera and or at least the mic, and you answer the questions. You come back. That's the advantage of online. I guess. You can do
Yeah.
these things as far as one can manage them. Yeah. I did send you the Jordan. I did send you the that information about
Okay.
Moses talk.
Okay.
It
good.
has a link which will have the other link. I think that's what they said. But I'll forward it to you when I get it 5 minutes before the talk.
Okay.
Good. Enjoy, guys.
All right. Thank you.
One funny example of causality. I just wanted
Uh-huh.
to add some funny thing to your example. If you
Yeah.
if you shoot a person that is about to die, let's say you shoot from, let's say 200 feet, and that person is about to die, then you get shot after you die.
Yeah, true. Okay. So the statement is not precise enough. You should die because of the bullet, right?
Yes.
Yeah, causality. The bullet has to cause the death.
No.
Yeah. Okay.
What we could
My
say
fault.
is
my bad.
what we could say is the bullet is, you're not gonna get shot until the bullet leaves the barrel.
What? You're not shot?
You don't get shot until the bullet leaves the barrel, the gun's barrel.
Oh yeah.
That's correct.
So it's not possible to get shot and then have the bullet leave the barrel.
Yeah,
That's
yes.
correct. Yeah. That's a more true statement. But then that's too much. I think people have to imagine. But I mean, this conveys the idea, I think. And then, of course, this is also good. Then there are there are flaws in the statement. That's good. I mean, I think nothing wrong in me saying it. And if people come up with this, they're thinking about it. This doesn't really work. So it serves the purpose, I think.
Oh, it sounds.
But good point. Very good point.
Sounds like you cannot go to the past and change the future. It does not seem physically possible.
If you respect causality, see, notice that. How to put it? If velocity is confined to speed of light and 0,
Mm-hmm.
then you cannot go to the past. That's true.
Right.
But what if you can go faster than light?
It's possible.
We don't expect it. Nothing we have seen does it. We don't expect it at all. But again, there is no reason not to expect it. It's just a bias that one has. But if you can go faster than light, then you can go to the past.
It sounds like sounds like in a one-way river. Let's say in a one-way river.
Mm-hmm.
Let's say we have a boat, and let's say the river is flowing at this, let's say 20 meters per hour, 20 meters per second. The speed of river stream is 20 meters per second. But if you have a boat that can travel at 10 meters per second, you cannot go the stream of the river will flow you further, and you cannot go, let's say you cannot go to the north, you just go to the south. But if your boat can travel at the speed of, let's say 30 meters per second, then you can go to the north. Sounds like it's possible
That's
for
not
the.
a correct comparison because there you're linearly adding. That's not correct, actually. That's not what we are doing in relativity. Remember, that's Galilean relativity.
So I have a question.
Let me just add one statement. So you have to use the Poincare velocity addition, and that's the counterintuitive part to that. And then there is a maximum limit to the speed. So you cannot go beyond a certain speed. So which is more than what you are saying, Avinash. That's linear, like A plus B, A minus B. That's Galilean relativity. Okay. So maybe you want to think about it a little more.
Okay.
Yeah, but yeah, that's good thought. Yeah, can you go in the opposite direction? So can you go to the past by staying yourself within the speed limit? And the answer is no. It is easy to show that it's not very hard. But if you go faster than light, then you can change the direction of time. You can get a cause, like causality is no more respected.
Will that website that you gave us, the Professor Kotick's website?
Yes.
I'll try in that one and see how it goes.
Yeah, sure. Yeah, that talks about only velocity, remember. You cannot go back in time there. Yeah, but that's good. Yeah, I think you're thinking correct. Yes. Yeah. Yes, Jordan?
So if you look out into space and, each dependent upon where you are, you have some observable universe that your bubble that you're within. But beyond that, there's more space and stuff and light and.
True.
Well, if the expansion of your observable universe is expanding at the speed of light, yet there's stuff outside your observable universe that's also expanding at the speed of light.
Yeah, you will never see it. In
So
fact, you don't have to go that far. I mean,
so we never know how big the universe is.
Yeah, but you don't have, see, that is more straightforward in a sense. But I will give you an example. In your homework, this will be part of the final homework that you will have. You will attempt a problem where the particles will come as close as a meter away from you. So there are two particles moving. Okay, they have a very specific motion. They will be accelerating, but their motion will be such that they will be standing right next to you. Okay, delta next to you. They can come as close to you as possible, but you won't know their existence. It's possible to construct such scenarios in relativity.
Is it because of the light thing?
Because
of the behavior
if you want
of
to
light?
interact with someone, you have to send light and it has to come back to you. Okay, so you can construct examples where particles come very close, delta close, but they will never know the existence of each other with a very specific motion. So don't take it too literally, but that is along the lines of what Jordan is saying. We don't see some part of the universe forever. Yes, of course. Like our universe, it doesn't have to be outside of the universe. We don't see part of our universe because we have lived only for a finite time. Universe has a finite time. And I can even stretch it to the case that you live for infinite time and still you won't be able to see certain things because light is having a finite speed. Very counterintuitive, but this example you will do, which is easy to see, and then that will take, oh yeah, this is possible. Once you accept that this is possible, then so many things are possible. Yeah, so good point. I mean, if you get curious, go into electromagnetic course of the semester. There is a problem in their midterm 2, right? Which is now you can actually.
This semester?
Yeah, this semester, electromagnetism, where Anjula is sitting in that, or is taking that course. Midterm 2, I think is first problem or second problem, one of them. There's a diagram there, it's very clear. Very qualitative, you should be able to answer that question now, which will show up in your homework also. But if
I
you
have a
get
question for
curious,
you too with index notation. Is there like, do you know of a good resource that kind of covers it
yes,
holistically?
I've been asked many times, and recently I did find a good book. Let me, a very tiny book. Hold on, I forget the name of the book. Let me, since I'm at home, I can just pull it out.
Hey, Moses, I got the email. Thanks.
No problem.
Assuming that I can get that book. Too many books. Vectors. Well, I don't see it now. I thought I had it. I don't see it, but then there's so many of them there that you might be missing it. Yeah, I'll find out and let you know.
I
Okay.
have one question. Could it be
Yeah.
could it be there is, let's say, some particle that travels faster than speed of light and we are not noticing it?
Possible.
I've heard of that the tachyon thing. So what's the deal about it?
Tachyon is the name of a particle that goes faster than light. As of now, we have never seen such a thing. And the bias, I would say, if I don't know whether yeah, there are reasons. Yeah, there is no strong reason, but generally seems like it shouldn't exist, mainly because of causality. Yeah, this is the point. For some reason, we like to preserve causality. And why? Because if causality was not there, it will be crazy. Okay. There is no reason otherwise to not accept it. It's just too crazy if causality was not respected. But is there a fundamental reason why causality should be true except for entropy? I don't think so. Like, again, I don't want to make those statements.
Well, if we
I
look
would
at
say keep yourself open about it. Read about
if
it.
we
I don't
if we
want to
look at the history of how things have changed, could be that we need to fix causality, the definition or the idea about causality a little bit to fit in the particles that can travel faster than speed of light. Maybe.
Yeah, of course you can change that, or maybe this is the way. By respecting causality, we have been able to explain so many things. Right? That's the big bias, and there is a good chance, or what one has to prove, which is probably very hard, is that if you violate causality, you should be able to explain everything else, and that's probably trickier, I think. So,
I heard that CERN made a faulty, how should I say, faulty measurement, and they said that tau neutrino traveled faster than speed of light at one point, and a few days after they
that's
said,
correct.
hey,
I remember that.
wrong.
I remember that. Yeah. But that's faulty, right?
They said it was faulty.
Yeah. Or you will face a lot of criticism if one should be open about it again, but it's not expected. Everyone will be very surprised if you come and say that you found something going faster than light. But remember that one has had such big revolutionary ideas. Einstein's idea itself was revolutionary. It was not obvious immediately that this will be true, but if it is really true, then one accepts it. It's very obvious that, okay, it will be true. But just by saying that, oh, it is possible, that's not sufficient. You have to convince more than that. As of now, it seems like it is not necessary to introduce tachyons.
Why do you think we haven't had another Einstein? in recent years. Another person like him.
Oh, I heard there was a lady from somewhere, I think in Harvard, who is often called as the next Einstein. Young lady. I don't remember her name.
See, this
I've
is
seen it.
sociology also. So I would also say that, okay, with all respect for Einstein, like Einstein was great, perfect. I mean, he did great things. But there have been very good, others did great work too. But he did get a lot of star
Oh,
attention.
I see.
And I would say it's all related to Eddington. Eddington was a very reputed scientist, English scientist. And after the eclipse, like until the eclipse, he was not as big a star as he is now. Like currently, he takes almost compares with movie stars, sort of. So until Eddington wrote a popular article in which he gave all the credit to Einstein, which he deserved, and that somehow made it into social circles. So that I would say is sociology, the kind of attention Einstein's ideas gets is sociology to a certain extent. There are lots of great ideas, I would say, without demeaning Einstein. Einstein did wonderful, but there are other ideas also are equally great, but then they don't get as much praise as Einstein gets. It's like a movie. Think of a movie that is a blockbuster movie, and there is another movie that hardly makes business. But one could argue that this is also good. So that's a little sociology in it, how people take a certain event or certain idea, and how it goes from one person to the other, how it is spread out.
Didn't there seem to be though, like in the early 20th century, early mid and late 19th century, people like Gödel, like just seemed to be like a vast array of people like that at the time.
Yes, that is correct. No, you're right. See, whole of fundamental physics or theoretical physics or fundamental science between 1890 to 1930, right? There were too many things that happened. That's just coincidence. It seems like it's just coincidence. And that was quantum physics and Einstein's relativity that came up. That changed the whole physics.
But even like incompleteness theorem, stuff like that, like all that stuff seemed to be around that time.
True. That's also correct. Yeah. There are many such things. Okay, you can say that they were brighter. Maybe the environment was right enough. But it is also, okay, here's the other side of it. We are not living in a time when these challenges are not there. One typically argues that 1900 was a time when there was so much discrepancy. For example, there was this ether theory sitting there. Everyone was struggling with it, and there was no clue how to explain it. Speed of light was measured in an experiment, and it was not depending on the medium. Big hit to theorists. They were not able to explain this. So there was the reason to work. But then we are in equally ripe place. I always say that dark matter and dark energy, think about it, it cannot get simpler than any of those concepts. And here we are missing 95% or let's say 70% of what we observe and what we experimentally see. And young people, clever people are thinking about it, and they're all failing. Okay, they have no clue what to do. So we are in that age, and it won't be very, the only difference is that this problem has remained open for too long. Usually a big challenge comes up and it gets solved in 10 years, usually 15 years. But this has stayed open for too long, like dark energy, dark matter. But maybe because we are too much biased with the existing physics. So young people like you guys have to think out of the box. We are in that region. Like we don't have any idea of what dark matter is. No clue.
But there's not a lot of jobs outside or thinking outside of the box. It's like
well, if
basement
Einstein had thought like that, he
physicists.
probably. If Einstein had thought like that, he probably wouldn't have come up with that theory, right? He didn't have a
Yeah.
job actually. He was not an academician.
Mm-hmm.
He was outside the circle. So I say there are open problems, very reasonably straightforwardly stated problems which has no solutions. So we are in that regime or time. And whenever that is solved, I think, personally, I feel that that will be revolutionary shift of paradigm. I think that's yeah. Helps. So you guys need to think, yeah. Typically, people say that once you're old, it is statistically speaking less likely that you will think of clever ideas or revolutionary ideas. So I'm a little late, but you guys are still in that time period, age time.
All I can say is Moses the Redeemer will shed light upon.
Tell that again.
Moses the Redeemer will shed light on dark matter so we can understand.
That's a joke between you guys.
What happened?
It's a good joke. It's a good joke. Never gets old.
Okay,
It has been here for more than 2,000 years.
it's true. Well, thank you for your time and for your extra time talking with us.
No, good. This is nice. Yeah. And
I'm gonna
Yeah,
solve the
good.
questions of dark energy and dark matter during my
correct.
my time today.
During your help desk.
And Riemannian, add to that list Riemann's conjecture.
Oh, on what? Sorry, you cut out.
Riemann conjecture.
Oh yeah, I'll do that too. I should be able to solve that in a night, just like
Yeah.
Newton
There's
did
a
the
long
problem.
standing open problem, I think, and which has been popularized, which has a price associated. Honest standing typically doesn't stay open these kind of problems.
Yeah, I'll work on that.
Your audio cut out, Chajesh, for some reason. I can't hear you. No, I can't hear you.
Maybe your battery died.
Yeah, I think my battery died. Okay,
Oh, there we
hold
go.
on.
There we go. There we go.
Did you get it?
Yep, we can hear you now.
How is it now? Now I'm using the laptop battery. Laptop.
It's actually
That works.
better.
It's
Yeah,
what?
yeah.
It's better actually.
It's better. That's because the battery was dying. So if I change the battery, I think this works much better. You guys have told me that this works much better. But maybe while it is dying, the computer is better. Yeah, I'll switch the battery. So yeah, I should have been more careful. Yeah, good. Okay, but yeah, let's disperse and yeah, feel free to talk whenever. Yeah, take care. Don't
Alrighty.
let people stay out of their houses, Jordan. So you build houses for people? Is that what you do?
Part of what I do, yes. Yeah.
Okay.
And none of that stuff slows down during, when everybody's home seeing projects that need to be done,
Yeah.
they call people that can do projects, unfortunately. And then employees, a lot of employees don't have to show up. So the time and busyness of all that adds up pretty substantially, unfortunately. But if if you want to enjoy something like this is what I enjoy, I have to put in time doing the other stuff. So it's, it's worth it.
Yeah. Yeah, these things are hard, but you're doing it. So give it the patience, I would say. I think first year you tend to more, you expect more. Like at least I can tell it from my research thing I was telling in the beginning. In the first few years, I thought, oh, I can do research while I'm teaching. But then I used to commit to people and I never used to get things done. But then eventually I realized that don't commit. Just think about it at your own pace. And I just don't commit to anyone that I'll finish this.
Mm-hmm.
It works fine. And people have patience. In academics, at least, people have patience. In your circle,
No, there's no patience.
you don't get your work house done. People get angry.
People want roofs.
Yeah, true. That's correct, actually. Yeah, so I take back. Yeah, I've been lucky to be with people.
It's slowing down a little bit, but it's
Moses, you can leave if you want. I think you might.
Okay.
You want to.
Yeah, I might do that.
Yeah.
See you guys later.
See you, Moses. Good luck.
Thank you.
Hopefully I can watch. Okay, bye-bye. But yeah, I think it's, in terms of completing things right now, I'm doing my best, but it's very difficult. I'm just trying to make sure that I am learning. That's the main goal.
Yeah, I think that should be fine, I think.
Yeah, I'm catching, I'm at all the lectures and I'm putting in as much time as I can type deal. So, it is what it is. And it's a privilege for me to be here. And that's the way I have to continue to look at it. It's not a chore, it's a privilege and I enjoy it. So I'll do whatever I can to make it through type deal. So.
Yeah, and I think I'm sure the department will be supportive. And it's necessary, like motivation plays a big role. Sometimes when you're working on research and you have something important, then probably motivation takes you farther than the amount of time you put in.
Yeah, I think the motivation is the only reason that I'm here. Because if I wasn't motivated, I would choose the easy path, which would be just not to do this at all. And
it might be a little harder the first few semesters at the coursework, but I think when you start research, presuming that you will do research.
and I was just getting into the swing of things before Corona, before COVID came out, and then that just kind of threw everything to the wayside. Assignments I was turning everything in on time and it was easy, but now it's gotten progressively harder and not so much the coursework harder, just, there's a lot of time constraints and it's just harder to work from home in general. So like when you have an hour in your office at SIU or an hour here, the difference in the amount of things you can complete in that 1 hour is vastly different.
Yeah, I think I know what you guys are talking about. I think Avinash puts it very bluntly. He says, I just get dumb at home.
Yeah, exactly. I am getting dumb and dumber.
He puts it really bluntly. And I think outsiders, believe it or not, I mean, including me, I think it's hard to convey that idea. I think I can associate with that. I know what you guys are meaning, but I cannot quantify it. If you tell this to a third person, probably they don't understand it. They think what you're talking about.
Yeah.
Including teachers. Teachers must be thinking, oh, these people are sitting at home. They have all the time. Why should they be watching television? Come on, we need to give them more homework.
Yeah. I think that's the wrong motive. Unfortunately, it's.
Yeah, but I mean, it's hard to get that point. I mean, I think you have to articulate that much better. Avinash, you cannot say that I'm getting dumb. You have to articulate it better.
It's
Right?
just,
Not easy
it's
to
just,
say that.
no, it's just that when I'm inside of the apartment all the time, my eyes just get heavy head, like my head just gets heavy and I cannot think.
I know, I think I know what you guys are saying, but I think one has to make this better, convey this better. Otherwise, a normal person will not understand it. I think I know what you guys are talking about. I don't know how to put it in words to a third person.
Okay.
Like I've tried convincing, like sometimes there is a discussion and between my colleagues and I bring this up and it is hard to convince that no, students are having less time kind of.
It's especially worse, you know, normally what I would do if I had an online course in the past would be, if I had something that needed to be done, I would go either to the public library or Southeast Missouri State's library, just sit in a corner and work. And it would be similar to being in the office at SIU. But when you sit at your desk at home, there's so many distractions that, you know, for instance, I was sitting at my desk a few days ago, and my father called me and said he was working in his yard. He needed someone to help him move a bush. He was digging up a bush and moving it to a different location. It was like 150 pounds. So he needed somebody to help him move it. And so, of course, you know, my thought process is, well, my dad's 63 and he's going to get the bush. He's going to get the bush moved either way. It's probably best if I just get up and go help him. So I went over to his house and helped him move the bush, which that would have never happened if I was at the university or an hour away. You know,
You gave a better example the other day. You said that I'm sitting here and I see the grass in front in the lawn and I feel like I have to mow it. I feel obliged to mow it. That's a good reason. And that doesn't happen if you are in the university. I know what you're saying.
Or you're sitting here and you're thinking, well, I'm hungry. Well, if I'm at the university, hungry means get in my car and go drive somewhere and find some food if I didn't bring food. Hungry here means I open the refrigerator 5 times every hour looking for something that's not there. Just, you know, and then my desk gets full of just junk that I have to clean up because my wife comes in and looks at it and says, "You're a pig." And you know, so it's, and then the time you actually get to sit down at your desk, like for me, whenever I actually have the time to sit down and work on something, it's the quality of the time is sufficiently less good than the quality of the time is in a distraction-free zone, where I think if I'm in my office, this is a work environment, like I'm getting work done. Before then, my desk at home was not particularly a work environment. It was just like a place to sit down and do a little bit of research, a little bit of reading. You know, it's not, you know, since I've had this desk, it's not been, I sit here and work, grind, but it's had to become that, and it's confusing to my mind.
Well, this has to be discussed. See, there is this whole concept of work from home, right? And apparently in some other sectors, like IT sector, for example, in software sector, it's very common and it works out well for people and for the companies. But I don't think it works surely in academics, apparently.
No, it does not.
And at least not for certain people. Like we don't have to say that in different sectors. It might be people dependent. So one has to be careful when someone uses these arguments, especially at policy level.
I think for something like technology, though, the answer is there. There's not a lot of rigorous problem solving. It's section A executes certain operation that solves most of the problems for what we're looking. Execute this function in 5 minutes, and then you do it and it's over and it's done with, and then you just sit there and look at your screen for another 4 hours. Whereas if your objective is to learn or to solve some unknown problem, to you at least, it's much different. There's many.
Distractions are here there.
Yeah, they are. If you're sitting, I can't remember ever getting up in my office because I saw a spider on the ceiling to go smash it. But if the spider is on the ceiling of my house, I'm more likely to get the chair out so I can reach the ceiling and then, smash it. Then I have a smashed spider guts on my ceiling. So now I have to spray it with something and clean it off the ceiling,
Yeah.
I would never do that in my office because it's not my own. It's just a function of work. That's it. It's just a function of work. That's it. I can't tell you how many times walking from the 4th to the 5th floor at SIU thinking like, man, I wonder if they've ever actually swept these stairs because they're so dusty and dirty. And the corners of the hallway or of the stairwells are super dirty and cobwebby. And I'm thinking, I don't know if anybody ever comes in here and cleans this. But if those cobwebs started to build up in my own house as I'm walking up my stairs to come to my office at home, you better believe I'm getting something out and cleaning the cobwebs. There's just many things like that don't exist in a work environment that do at home. And it's you can learn at home, but it's less efficient than it is, especially the environment of doing homework. I can't tell you how many times I get stuck on a homework problem, especially on the quantum homework right now that we're doing. Just, you get lost, you're like 4 pages deep and you made a mistake and you're not even sure how to go back and look. And then without somebody next to you that's working through the same material as you to help you, say like, oh, it's easy for me to see the mistake because I made that mistake 2 days ago, and then so-and-so helped me so I can help you. It's just that interaction is just not there, and it's unfortunate.
Yeah. But hopefully this is all temporary and not more than may end, I suppose. Hopefully, we are optimistic.
All I can hope is
We're gone.
things come back to normal next semester.
Yeah,
I don't even know. I don't even know what's gonna happen to my graduate application.
Yeah. There's so many uncertainties. Yeah. I feel the virus will be with us, but probably at least this semester part, at least the learning part, the university probably will start functioning normally. That's
my biggest fear, for instance, in the quantum class, like he had more of it wasn't just a QNet course before, his QNet. It was much more than QNet before it went online. And then when we went online, it's just a regurgitation of QNet, which isn't really the course that he's teaching. 'Cause now it's more just like quantum computing stuff that we're doing. And it wasn't really that before, which is even a little bit farther advanced than I was previously. I already had a relatively poor experience in quantum in undergraduate, and then going 4 years without a quantum course. I was okay, and I understood most of the linear algebra stuff, but we even strayed from standard, Schrodinger equation stuff and just went into quantum bit flips and quantum error correcting, which I have zero experience or background with at all. So my fear is like I'm missing. There's missing links in my understanding of quantum at the moment. So hopefully come second semester, he doesn't, he understands that the people that are in the course currently are going to be probably behind. And he thinks we're really smart, because we had a take-home exam and we all had 24 hours to work on it. He said, wow, you guys all did really well on the exam. Well,
Oh, good.
he also told us that he gave essentially the exact same exam he would have given in class in a 2-hour period, which we all worked on for about 15 hours. So he said, wow, you guys did really great on this exam. And I'm thinking, if this was a 2-hour exam, my score would have been significantly worse. But I will say from an exam perspective, I'm learning more in that way. Like thinking about a problem and letting it play out is beneficial, as opposed to just trying to learn how to solve a problem and regurgitating information. I will say that it's, to me, I'm
That's
learning
good.
more from exams than I am from
Good. Yes.
what I would in class.
Yeah, that's, I think, at least what I also say, that an exam should not be taken by memorizing whatever has been done and reproducing. Instead, that should be a different problem altogether. And use, I mean, at least my perspective is that I get 1 or 2 hours of a student where the student is completely focused.
Mm-hmm.
So if I can utilize that, that will be great for learning. That will be great. But it's hard to make such problems, honestly. Yeah.
Especially the more difficult.
Undergraduate level.
Yeah.
Undergraduate level students are not prepared for that. They don't accept it very easily.
And I think but I think too, in like an undergraduate level, some part of it is like, hey, here's a kinematics equation. There's things you just kind of have to know, and then you can build off. Okay, how do you develop the kinematics equations? If you can teach a student to do that instead of saying like, here's the 4 equations that you need to know in kinematics, instead take the derivative and the integrals and then develop the equations yourself. I think that is often missed in courses.
Yeah, I have tried this a little. Earlier, I used to do it a lot more. And these days, I confine to just reproducing the homework, because I think what happens is that many of the undergraduate students need not be highly motivated to be doing physics at a research level. They are more there to study the content that's provided to them. And it's not that they're not smart or anything. That's not their priority. They might be spending their time in studying some other subject. So I have taken a backseat and I have come back to the traditional approach where you give them homework and then ask problems very closely related to homework, or basically don't surprise them.
No.
What you're saying is to surprise them and then let them critically analyze the problem. That's great. That's perfect. That's what I used to like. But I think at undergraduate level, it becomes a little overburdening for the students. I think so, at least in SIU.
Yeah. I can only speak for myself, but I really enjoy, if you're going to give me, so say you were to give me an exam and I had a choice, and you were to say, okay, you can take an exam, it'll be 4 problems long, but the problems will be relatively simple, and you're to complete it in 2 hours. For me, I would not really, I'm not much into that. I'm more into the idea of like, here, take this thing home. These are really hard problems that you're not going to find on the internet, and I want to see how you think. That's and not getting the correct answer is okay. It's like identifying the process of thinking. Like for me, some of the problems, even on this exam that you gave us, I didn't know if I had to complete that in 1 hour and 50 minutes, I probably would have struggled a little bit, just because I had to think a lot about what's going on with these gears, or what's going on with the Kepler problem. And it's more beneficial for me to take an extra hour per problem and just process and think, make errors, go back, make corrections, because I made lots of errors, and there's still probably errors but I spend a lot of time on each problem. And to me, as a learner, it's more beneficial. And unless your only goal is to turn out like the smartest of the smart people, which is unlikely with who you get at somewhere like SIU, the goal should be teach these people how to do physics, because, you know, that's what they're here for. But I think we get stuck in the mindset of like, hey, we need to, you know, we have to gauge where our students are. And then
Yeah.
maybe it even pushes out someone who's more of a long-term thinker than some short-term regurgitator,
Mhm.
which I think I'm more of a little bit. I'm already a slow test taker. I like to think about problems.
These challenges come up at an assessment level. I agree. So
I think you're doing a good job, and I appreciate the work and the effort you put in to do setting up this in your home for us. It's far better than
this works
what I
out, I
expected.
suppose.
Yeah, it
Better,
does.
actually.
It's nice being able to go back and review, and, you know, if you miss something, you can go back and look at the videos, and so it's beneficial. That
Earlier,
I
was a
can say
little-
is beneficial.
Yeah. Earlier, I was a little apprehensive that, oh, I'm making mistakes in all this lecture. Then I thought, okay, it's okay. As far as the mistakes are not deeply conceptual mistakes, I don't care. Factor of 2 here and there, it's okay. It's going to be there for life.
Yeah, that's okay, because that's how you learn either way, you know?
Yeah, so,
If you
okay,
make a
that's
mistake, the next time you do a course online, you fix it, and then eventually you become, you know,
fine. Yeah.
Gödel. There you go. Gödel's theorem. So, well, I appreciate it. I'm off to my help desk hours now. Thank you for the
Okay.
conversation. It was refreshing.
Okay. Have a great day.
Okay. Take
See you,
care.
Avinash.
Okay.
Yeah. See you. Bye.
Dr. Shajish.
Yes, don't stay dumb, Avinash. Be bright.
Bye-bye.
Bye.
Take care. Bye.